Let's be honest, your body is the most sophisticated machine you will ever own, hands down. And right at the heart of it all is this masterfully engineered pressure management system, working around the clock to keep you alive and, well, upright. So today, we're going to dive into exactly how it all works.
I mean, have you ever really thought about that? It seems like such a simple question, but the answer is anything but. Why is it that when gravity yanks blood down to your feet, you don't just crumple to the floor? Well, the secret is a series of lightning-fast controls that manage your internal pressure with just unbelievable precision. So how does your body pull off this magic trick?
To get it, we have to start with the one number this whole system is built to protect: your mean arterial pressure, or MAP for short. Just think of MAP as the steady, reliable pressure that makes sure every single one of your organs, from your brain all the way down to your toes, gets the oxygen-rich blood it desperately needs. Keeping this number stable, well, that's the whole game.
So how does the body actually control this pressure? It really boils down to this one fundamental equation. Blood pressure is just a product of two things. First, how much blood your heart is actually pumping out. We call that cardiac output. And second, how much your blood vessels are squeezing back. And that's systemic vascular resistance. So let's break down each part of this super elegant formula.
Okay, first up, the pump, the engine room. And your heart isn't just some simple squeeze box. Oh no, it's more like a perfectly timed two-part symphony of contraction and relaxation that powers absolutely everything. And we call this the cardiac cycle. So this cardiac cycle, it has two main acts. First, you've got systole. That's the big, powerful contraction phase, the push. Then you have diastole, which is the equally important relaxation phase. That's when the heart gets to chill out and refill for the next beat. And get this, when you're just resting, your heart actually spends about 2/3 of its time in diastole, just relaxing and filling up. It all kicks off with something called isovolumic contraction. It's a fancy name, but all it means is that the heart's main chambers, the ventricles, start to squeeze. But here's the key. All the valves are slammed shut. So for a split second, it's a completely sealed box. And you can see on the graph how the pressure inside just skyrockets, building and building for that big push. Then, once that pressure inside gets high enough, boom, the exit valves burst open. This is the ejection phase, and blood is literally launched into the body. The really cool thing to see here is that light blue line on the graph. That's the heart's volume, just taking a nosedive as the chamber empties out. Then, the ventricles relax, and the pressure just plummets. Now, to keep blood from flowing backward, those exit valves have to snap shut. And that closure creates this tiny little pressure blip in the aorta that you can see right on the graph. It's called the dicrotic notch. It's kind of like hearing the sound of a door slamming shut after each heartbeat. So we know how the heart pumps, but how do we measure how much it's pumping? How do we actually put a number on its performance? Well, that brings us right back to the first part of our main equation, cardiac output. Cardiac output is super simple. It's just the total volume of blood your heart pumps out every single minute. It's the ultimate performance metric for how well your heart is delivering oxygen to your body. But that raises a pretty big question, right? How in the world do you measure this inside a living person without, doing major surgery? Well, the answer comes from a 19th century physiologist named Adolf Fick, and he came up with this brilliantly logical way to calculate it. It's just a fantastic piece of scientific reasoning. The logic is just beautiful. Imagine your body is a factory. We know how much oxygen the factory uses every minute. We can also measure the oxygen level on the delivery trucks going in, that's your arterial blood, and the oxygen level on the trucks coming back out, that's your venous blood. The difference tells you exactly how much oxygen each truck dropped off. And from there, you can calculate precisely how many trucks or how much blood flow were needed to supply the whole factory. And that logic, that whole factory story, translates directly into this equation. Cardiac output is simply the body's total oxygen consumption divided by the difference in oxygen between the in blood and the out blood. It's a totally ingenious, non-direct way to measure the heart's total output. Okay, we've covered the pump. Now, how does the body control all of this stuff on a second-by-second basis? Well, for that, it uses a dedicated rapid response team of sensors. These sensors are called baroreceptors, and they are placed in some very strategic spots, like in the major arteries going up to your brain and in the big artery coming right out of your heart. They are constantly monitoring the pressure just by sensing how much the artery wall is stretching. They work on a simple but incredibly powerful principle, a negative feedback loop. It's just like the thermostat in your house. When the room gets too hot, the system kicks in to turn the furnace off, right? To bring the temperature back down. It's the exact same idea here. When your blood pressure gets too high, the baroreceptors fire signals to bring it back down. So let's go back to our original question. You stand up, gravity pulls blood down to your legs, and the pressure in that artery going to your brain drops for a split second. The baroreceptors feel less stretch, so they send fewer signals to the brainstem. The brainstem immediately goes, whoa, red alert, pressure is low. It cranks up the sympathetic nervous system, which tells your heart to beat faster and your blood vessels to squeeze tighter. And just like that, within a heartbeat or two, your blood pressure is right back to normal, and you didn't even notice. But that baroreflex, that's a short-term fix. It actually adapts over time. So for managing blood pressure over hours, days, and weeks, the body needs a totally different strategy. It's got to play the long game. And this is where the kidneys take over, with a system called the RAS. You can think of the kidneys as the long-term managers. When they sense that pressure is consistently low, they trigger this whole hormonal chain reaction. This cascade does two really key things. It constricts blood vessels all over the body, and it tells the body to hold on to more salt and water. And more water in the pipes means more volume, and that brings the pressure back up for the long haul. So, when you put it all together, from the perfectly timed beat of the heart to that rapid-fire baroreflex and the slow, deliberate control of the kidneys, your body is conducting this impossibly complex symphony 24/7 just to keep your blood pressure stable. It's a constant, delicate balancing act. And it really leaves you with one final thought. What other incredible feats of biological engineering are quietly at work inside you right at this very moment?